Hello, this is Bryant Myers, author of PEMF, The Fifth Element of Health. In this video, we're going to continue talking about magnetic fields and how they arise from current loops, even at the atomic level. And we're going to look at the equations used to calculate magnetic fields, which is the Biot-Savart law and Ampere's law. And finally, we're at a point where we can expose the really big lie in PEMF therapy. This is probably the most important video in this series, so I'm excited to get right into it now. For thousands of years, the only known sources of magnetic fields were certain iron ores like lodestone and other materials that had been accidentally or deliberately magnetized. Well, that all changed in October 1820 when Hans Christian Ørsted accidentally discovered that an electric current produces a magnetic field. He noticed that a compass needle was deflected near a wire and moved when an electric current passed through it. This suggested that the current in the wire was producing a magnetic field that affected the compass. Shortly after this discovery, French physicist André-Marie Ampere heard about Ørsted's discovery, and within a week, Ampere began quantifying the relationship between electric currents and magnetic fields, which, as we'll see, is called Ampere's law. So within a short period of time, electricity and magnetism became forever connected at once in one field to study, electromagnetism. Now here's what Ørsted found. Whereas stationary charges produce an electric field, moving charges in addition produce a magnetic field. In fact, magnetic fields are easier to detect. All you need is a Boy Scout compass. Now if you hold a tiny compass in the vicinity of a current carrying wire, you'll quickly discover a very peculiar thing. The field does not point toward or away from the wire, but rather circles around it. In fact, if you grab the wire with your right hand, with the thumb in the direction of the current, your fingers are curling around in the direction of the magnetic field, and this is called the right hand rule, which you can see from this image. Now back to Ampere. Ampere was experimenting with some wires trying to learn more about the connection between currents and the magnetic fields they create. And here's what he found. When he took two parallel wires and ran a current through both of them in the same direction, the wires attracted each other. When he ran a current through both wires in opposite directions, they repelled. Because both wires are electrically neutral, which is obvious when the current is turned off, it is not electrostatic, so Coulomb's law does not apply here. What Ampere found was that magnetism is caused by moving charges and felt by moving charges. And the Lorentz force law equation quantifies the magnetic force. When a charged particle moves through a magnetic field, it feels a Lorentz force F, which is the magnetic force, given by Q, the charge, times the cross product of the velocity of the charge and the magnetic field. So to get a visualization of which direction the force is created from the current or the moving charge and the magnetic field, this is the second right-hand rule. So hold out your right hand like this image. The current or the moving charge is going in the direction of your thumb, the magnetic field is going in the direction of your fingers, and the force is coming out your palm. So if you do this with the two wires, with the current going in the same or opposite directions, you'll see the force will be pulling the wires together in the case of when the currents are going in the same direction, and it moves the wires apart when the currents are moving in opposite directions. So this comes from the Lorentz force law. And again, if you don't understand that, that's okay. Just know that the magnetic force is more complicated than the electric field force because magnetic fields, they circulate or circle around the wire. They don't radiate out in straight lines, so it makes it a little more difficult to calculate. But as long as you understand that visualization, then that's good enough for now. Now we can see the units of the magnetic field from the Lorentz force law. A 1 Tesla magnetic field exerts a force of 1 Newton on a charge of 1 coulomb moving at 1 meter per second. So remember in the last video we looked at magnetic field strengths and some common everyday objects. So magnetic forces in action. Here's a couple examples. The sun is constantly shooting charged particles towards the Earth, and they would be very damaging to life if we didn't have a magnetic field. In fact, it would just sort of blow our atmosphere right off the planet. And what the Earth is doing with the magnetic field, because the charges are coming in perpendicular, they're getting deflected around in safe orbits. So we don't get all those charged particles hitting us straight on, which would be devastating for life. Another example of magnetic force is PEMFs are creating a changing magnetic field, but that magnetic field is moving charged particles in your body. And mainly, as I've showed in other videos, it helps to energize the cellular voltage by moving charge, namely by moving sodium out of the cell and potassium into the cell to give a net positive charge on the outside of the cell. Okay, we've been talking about magnetic forces arising from steady currents and moving charges. Now let's take a look at the magnetic field itself that's generated around a wire. And just for simplicity, we're going to stick to steady currents moving through very thin wires. Remember in the last video, we explored the idea of magnetic fields very visually with like iron filings around a magnet and the basic idea of flux lines, where you have a greater density of flux lines, the magnetic field is stronger, and the lower density of flux lines, the magnetic field is weaker. So let's now quantify the magnetic field strength using the Biot-Savart law, which is the magnetic field equivalent to the Coulomb's law for electric fields. The Biot-Savart law basically says that every little segment of wire, which we call dl for a little small segment, with current I, will produce a little magnetic field dB, which is a small little magnetic field. Now this is one nasty little formula because unlike Coulomb's law, where the cause of the electric field is a simple point charge, the cause of a magnetic field is a tiny line segment of current. So we have both a direction and a moving current, so it makes it much more complicated. As we'll see, you're never going to get a 1 over r squared drop-off, even though it is a 1 over r squared law. Why is that? Because to get the total magnetic field, we have to integrate or add up all the magnetic field contributions of each little tiny line segment over the entire length of wire. And as complicated as it looks, if you can just understand that this equation is used to calculate magnetic intensities, then that's good enough for now. Now let's kind of take an example of a loop of current, which we use in PEMF devices. That's very appropriate. The Biot-Savart law is going to give us an equation telling us the magnetic field strength any distance from that loop of current. But it's easiest for simplicity just to take the intensity along the center axis of the loop. That gives us a 1 over 3/2 drop-off. And it's dependent on both the radius of the loop and the distance away. Notice this is not a 1 over r squared drop-off. This is one of the big lies in the PEMF community. So-called experts use a 1 over r squared relation to justify needing a high-intensity PEMF device. They're actually using the wrong equation altogether. A few examples, Marcus Freudelman, which I did a whole video, PEMF, the really big lie. Dr. Pollack, a very well-trusted and respected PEMF expert, companies like Curatron, they use this 1 over r squared relation in their books and articles to justify needing high intensity. I'm not trying to pick on Dr. Pollack, but I just want to take this chart from page 13 in his book, Power Tools for Your Health, which is a very well-researched book on PEMF, but pages 10 to 15 where he tries to justify high intensity with a 1 over r squared law, I think we need to look at that. So see this chart here, and I'm going to do a separate video on this, but he does not use the Biot-Savart law to get these numbers. He's using a 1 over r squared law, and he's not even using it correctly. And you can see that because at 0 inches, remember 1 over r squared is the distance away, 1 over 0 squared is infinity. Remember that from math? So how can you get an intensity at 0 inches away? That's just, again, it doesn't even work. Secondly, not only is he not using the right equation, but he's not using the right units. He's using inches here in centimeters versus meters. You have to put meters into the equation to get the right result, or your dimensional analysis will be off, and you just end up with numbers that are gibberish. But just to give you a sense of how wrong his numbers are, you can see these numbers in green here on the far right-hand column. These are the magnetic field strengths of a 100 microtesla field using an 11 centimeter coil, which is what the iMRS uses. And that's the Beamer uses a coil about that radius as well. Now notice how the answers differ. So you go from 99 to 98 to 90 to 83 to 76 to 62. And again, I double checked these numbers. These are the field strengths you would get using the Biot-Savart law from an 11 centimeter coil. Now I want to call your attention to this chart in Dr. Pollack's book and look at 5 inches away. You can see that the answer is 0.5 microtesla. Compared to 62, that's just way, way off. And many of the PEMF devices on the market do use larger coils. So for larger coils like the iMRS and Beamer, that number that Dr. Pollack is listing is not just a little off, it's off by 10,000%. The reason I have such a problem with this is that he uses this in his book to justify that low-intensity devices won't penetrate all the way through the body, when in fact I've done many video demonstrations showing that they do. So this is just bad science, and it was really one of the motivations for me to do this course, because so many high-intensity PEMF companies and so-called experts are using this bad science to justify high intensity, which I call the really big lie. I'm going to do a whole separate video to really break this down. But just for now, know that you need the Biot-Savart law to calculate the correct magnetic field intensity. So that's the Biot-Savart law. So now let's talk about Ampere's law. Ampere's law is kind of like Gauss's law. It simplifies the Biot-Savart law in situations where there's symmetry. Basically, here's what Ampere's law says. If you draw a circle or any loop around a steady current of wire, the magnetic field will have a set strength on that circle. Ampere realized that the stronger the current running through the wire, the stronger the magnetic field that will circulate around the circle. Or more precisely, it says that the total magnetic field around a closed loop is equal to the current running through the loop times what's called mu naught, which is the magnetic permeability constant. We'll look at that in a minute here. If you're not able to follow this, don't worry. Just at least understand that a steady current produces a circulating magnetic field. And we use the right-hand rule to determine the direction of the magnetic field, and the Biot-Savart law, or Ampere's law, to calculate the magnetic field intensity in Tesla at any point in space around that source current. Now, the geometry and strength of the current determines the magnetic field strengths. And like I said, these are not point charges, so there's not going to be a 1 over r squared law. So here's a few examples. So if you have a long infinite line of current, it's going to end up being a 1 over r drop-off. If you have a circular current loop, like we said, it's a 1 over 3/2 drop-off, and you need both the radius and the distance away. And if you have an infinite sheet of current, it doesn't diminish at all. I mean, again, these are going to be similar to what we looked at with electric fields because they're both 1 over r squared laws, but when you look at the geometry of the source charges or currents, that tells you how the field strengths drop off in space. Again, what's really noteworthy for PEMF is understanding the Biot-Savart law or Ampere's law applied to a current loop. So now let's look at the permeability of free space. The constant proportionality between the magnetic circulation on the left-hand side of Ampere's law and the enclosed current on the right side is called mu naught, and this is the permeability of free space. Now, just as the electric permittivity characterizes the response of a dielectric to an applied electric field, the magnetic permeability determines a material's response to an applied magnetic field. So magnetic classifications of materials. In terms of magnetism, materials are classified as paramagnetic, diamagnetic, or ferromagnetic. Now, diamagnetic materials are weakly repelled by magnetic fields, but just very weakly. Usually it's like 0.999997 in the case of, say, gold, silver, or copper. Paramagnetic materials are weakly attracted to magnetic fields, but again, they're just going to be slightly greater than 1, like 1.00002. Now, ferromagnetic materials like iron and nickel, especially iron, respond strongly to magnetic fields. In fact, they increase the magnetic field very significantly, hundreds to thousands of times in the case of iron. Here's an example from PEMF. Some devices on the market, like the iMRS 2000, have a probe or pen applicator, which is essentially a solenoid wrapped around an iron core. Now, a solenoid has a magnetic field, if we use Ampere's law, equal to mu naught times the current times the number of turns of the solenoid divided by the length. In the case of the iMRS, it's about 100 turns, and the length is a few inches. Because the iMRS uses an iron core in the center, that's going to amplify that field strength that we found by Ampere's law, actually a couple thousand-fold. So this gives you a very powerful focused magnetic field, and you're not going to get that with some PEMF devices that have local applicators that don't have this iron core. So ferromagnetic materials significantly increase magnetic fields. Unlike electric charges, magnetic fields don't really diminish through material. Even through lead, magnetic fields penetrate. And remember, your body, the dielectrics are around 40 to 50, so you would divide the electric field by 40 or 50 in the body. And with magnetic fields, you're dividing it by 1. The magnetic field intensity is going to be just like free space, more or less. And this is important for many reasons. One is that this shows that PEMF devices are going to penetrate deeper and work better than electric current, which has impedance, electric fields, which has dielectrics, and photons, light therapy, which has penetration depth. So none of these forms of energy medicine are going to penetrate through your body like PEMFs will, or magnetic field therapy will. Basically, the human body is transparent to magnetic fields. Magnetic fields only diminish by these inverse relations that we talked about. But we do have trace amounts of magnetite and other ferromagnetic materials in the body, like in the hemoglobin, that can amplify very weak magnetic fields. And there's some really good research that I've shown in my book and elsewhere to show how the very weak magnetic fields of the Earth, especially the Schumann resonance, which is like in the picotesla range, can be amplified by these little magnetite deposits in the human brain and throughout the human body. So this is really fascinating to me, and it's one of the reasons why we don't need higher intensity, because our bodies are very sensitive and we can amplify these weak signals. So you can't shield magnetic fields like you can electric fields. And the reason for this is that there are no magnetic monopoles, meaning, remember when we cut the bar magnet in half, it just gave us 2 more magnets? So magnetic fields are what are called dipoles. They have always a north pole and always a south pole, and it wraps around. Now, if you ask the average person what magnetism is, you'll probably be told about your refrigerator decorations, compass needles, or the North Pole, none of which has any obvious connections with moving charges or current-carrying wires like we've been talking about. Yet, all magnetic phenomena are due to electric charges in motion. And in fact, if you could examine a piece of magnetic material under the microscope at the atomic scale, you would find little tiny current loops, electrons, little tiny magnets spinning on their axis and orbiting around the atomic nucleus. So magnetism at its roots arises from current loops, microscopic current loops, spin magnetic moments of elementary particles. This gives rise to magnetic materials, like the magnets you're familiar with. And macroscopic current loops, like solenoids or just rings of current like in PEMF devices, are all over the place to create magnetic fields, so we can use electricity to create magnetism. Electromagnets are an example. Many electrical devices like motors, generators, relays, solenoids, loudspeakers, hard disks, MRI machines, they're all using circular current loops to create magnetic fields. So doesn't it make sense, if you want to get a PEMF device to give you a true pulsating magnetic field, that you need a circular current loop? This is really important because some energy medicine devices on the market claim to be PEMF, but really are not. Let me give you a few examples. The Pearl M is a Rife machine that uses a gas plasma tube. They claim to be a PEMF device, but there's no circular current loop. So while you're getting maybe photon or electromagnetic type of fields, you're not getting pure pulsating magnetic fields. Another example is David Serrata's light stream mantra coil, which has these wacky windings and sacred geometry patterns. Again, they're not circular current loops, so you're not going to get a pure pulsating magnetic field through the center of whatever that geometry is. Another example is the Healthy Line and Biomat. Those are, using amethyst or different types of jade stones to give you infrared heat. Now that is, again, infrared therapy, but it's not a pure pulsating field. And the Healthy Line has these little dinky coils in their PEMF system, which really hardly makes it PEMF. Now the Metathera and the QRS, I do consider those PEMF, but they do use big oval racetracks with big spacing in between. So you do kind of get a quasi-magnetic field, but it's not going to be a pure pulsating field like, say, the iMRS or Beamer, or some of the other systems that use very tightly wound, perfectly circular loops. So again, you really need to get a device that has a tightly wound, circular current loop, because magnetic fields only come from current loops. You can think of the coils like the speakers of a stereo system. Would you buy cheap speakers with a really nice stereo? Of course not. Continuing the speaker analogy, you typically don't buy a nice stereo with just one speaker. So when it comes to PEMF therapy, you definitely want a full body mat with multiple coils. And the main reason for this that we really haven't talked about yet is that the magnetic field through a coil or a solenoid is only going through the center. In fact, with a solenoid, you only get the B field in the center of the coil. So a full body mat device will give you multiple coils to cover your whole body, so you're getting a pure magnetic field through the center of those coils. Unlike these one coil systems like the amp coil and the earth pulse on the market, you're really not getting much of a pure magnetic field unless you put that single coil on the spot that needs treatment. And good full body mat systems will have local applicators, but you do want a full body mat with multiple coils. Because the coils are so important and so little talked about in the PEMF community, I'm going to do a separate video because it's such an important point to understand that pure magnetic fields only come from tightly wound, perfectly circular current loops. And the magnetic field component of those loops is going through the center of the coils. So thanks for watching. In the next video, we're going to talk about Faraday's law of induction. And this is really important and has tremendous implications for PEMF devices. So stay tuned for that and have a fantastic day.